Okay.
Hey, good afternoon or good morning, everyone. Glad to have each and every one of you here. We're excited to kick off this new webinar series. We're calling the summer webinar series called "Keeping It Cool with Reliability." See, we've got several folks that's already logged on here, and thank you for each and every one that's joining us today. Um, we're going to get kicked off today with our first in our series of the myths and pitfalls of lubrication. Um, Today's going to be presenting is one of our instructors. He's been with us for a little while now. He's a really good guy, Brett Scott. He ton of experience in lubrication. So what he's going to be talking about today is it's not just off the top of his head. It's stuff he's been dealing with and been working around for a long time. So we're excited to see what he's got to say to us. This meeting is being recorded, and so we're going to probably once it's done processing, we'll make it available for everyone as well. So thank you again for joining. And Brett, if you'd like to get it kicked off there.
All right, thanks, David. So yeah, today I'm going to be talking about some of the lubrication things. I basically came up with about 5 different myths that I kind of come across that people tend to misunderstand with lubrication related things. So we have a new asset lubrication technician class that we're going to be doing publicly, and we've been doing some private ones currently already. I pulled just some of the slides from there to hit kind of the highlights of some of the things I think that people is probably misunderstood a lot. So I'll jump right in since we're going to try to keep this at 30 minutes. A few of you might see this and laugh right off the bat because I would be remiss if I didn't talk about the P to F curve. We're talking about predictive maintenance world. We're talking about reliability. You have to talk about the P to F curve. So I'll keep it brief. I'm guessing probably most people on this call have already seen this and understand what it is, but just in case somebody has not, and why this is important for all the different predictive technologies. So P to F curve, basically somebody came up with a plot showing the asset's condition over time from the onset of a fault type, let's say a bearing fault, raceway pit or something. We get dirty lubrication in our dirty oil, and a piece of contaminant gets between the raceway and the rolling elements, and it causes a pit in that raceway. It's kind of like a pothole in the road. The more times the wheels go over that pothole, the wider it gets, the deeper it gets, the more cracks and things that happen. That's what happens with our raceways and our rolling element bearings. So the initial, when that first failure begins, you're going to walk by the machine, you're probably not going to notice anything. Without the use of any kind of technology like predictive tools, you would not know that there's a failure started. No temperature changes, no sound change. You're not going to see anything, smell anything like that. But over time, what happens is we're plotting what the different predictive symptoms are that are going to show up from when that occurs to if we don't do anything to that thing and let it go all the way to catastrophic failure. So the first 2 things that really should be pretty close together, the first 2 dots you're going to see is ultrasonic and vibration. So ultrasonic, we could use UE systems or SDT type of ultrasonic testing devices. We can pick up this early stage bearing faults from just a general term, HFE, high frequency enveloping. Could be peak view depending on what kind of data collector you're using. But we're going to pick those up early. The next thing is it's going to fall into our regular velocity spectrums. We're going to start seeing some of these fault frequencies and other symptoms in our data. That's the next thing. If we still have not done anything to this bearing and replaced it or repaired it, the next thing that's going to happen is pieces of that pothole are going to be breaking out. Part of the raceway is going to start, pieces of it are going to come off and drop into the oil. And as we collect oil analysis, we pull oil samples, we're going to have more iron generally in that oil analysis report. So the iron count's going to go up. We might also see our ISO 4406 cleanliness code, just basically telling us how many particles are in the oil. That's going to go up as well. The next thing is going to be a temperature change. It's going to be a slight temperature change, probably not something you're going to pick up just by putting your hand on it. You might need a spot radiometer or a thermography camera or something like that. A slight change is going to happen. If left unattended even longer yet, which I hope we're not going to do that, but we get into the point where you start to audibly, you hear things. You don't need a data collector. You don't need an ultrasound. You don't need any tools. You're walking by. You can tell this thing's making a strange noise. After that happens, it starts to get hot to the touch. No IR cameras or spot radiometers needed. You're walking by. You can feel the heat on that bearing. And then the next thing, it becomes mechanically loose. Again, we don't need a data collector for that. You may feel it just walking by or standing next to it or putting your hand on it. And then ancillary damage, basically just meaning smoke's coming out of this thing. It's turned colors because it's gotten so hot. Blistering paint pieces are on the floor next to it. Again, you don't need, at this stage, you don't have to be an expert in any of these things. You walk by, you're going to know something's wrong with it. And then finally, the thing catastrophically fails. It either seizes up or completely explodes. So that's the path that these failures take, and the kind of the symptoms we can pick up along the way. So you can kind of see vibration and oil analysis very early in that stage. The further left on that P to F curve we can get, the less cost is going to be involved with repairing these things. So that's why if we can identify early, we can plan, we can schedule, we can have the parts ready, we can have the people that can make the repairs. We might even find out that we have an outage coming up where we don't actually have to bring this down specifically to change this. We can do it when it's convenient for us. So that's what this P to F curve is designed to do, to show us if we find it early, far to the left on this curve, we can take action and save quite a bit of money. If we let this go all the way to failure, there's going to be a lot more parts to replace and repair. The damage that does happen could even damage our structures and our bases and things like that. It just becomes more costly. So anyway, now that we've said that, and like I said, that's probably a refresher for a lot of you guys, that's what our P to F curve is dealing with. One thing you will notice on these, Vibe guys especially, on these P to F curves, you notice most of the time they don't have hours, minutes, weeks, months, days, years, whatever, as our time on our x-axis, because that's the first question everybody asks. I got a bearing fault. How long do I have? And as a Vibe guy, anybody out there that's doing Vibe, you know it's very difficult to give them hours, weeks, months, etc. What we can tell them is we've identified it early. We have some time. All right. Anyway, done with the P to F curve. We're going to cover a couple common terms and properties dealing with base oils before we dive into the myths. First thing is a couple lubricant types. The main ones, there's other ones other than these, but the two main that we're dealing with most of the time out in the field is going to either be a grease or just a lubricating oil. They have certain things in common. The lubricating oil is made from some kind of a various different base, which could be crude oil pulled from the ground and then going through a refining process. Could be a vegetable-based type oil, which a lot of times used with food-grade type lubricants, or it could be synthetic base, where it's basically made in a lab. It's created from chemicals and things like that. So that's our base oils. Then we add these additives and things to them. We formulate them so that they can be used in the field. And that's where the oils start to become different. The greases are essentially, they are oils, but they are suspended in a thickening agent. So what you can think of a grease, I think that's another misconception about grease, is because it's so thick, we're making the assumption that the main ingredient is the thickener, but it's not. Grease is actually 70 to 90% base oil. So it's mostly oil. That thickener is in there to act like a sponge. It's there to soak that oil up, keep it in place around the lubricating points that we need to have. So that's what our thickener is there to do. Our properties for some of these base oils, viscosity. I think everybody's probably familiar with that one. That's essentially how thick or thin the oil is. Scientifically, there's a little more to it than that, but in a 30-minute webinar, that's the definition for viscosity for today, how thick or thin the oil is. The next thing that we're going to talk about is the viscosity index, which is basically a rating of how well the oil behaves in temperature changes. So you think about honey. Honey at room temperature can be pretty viscous, pretty thick. We heat it up in the microwave, it becomes very thin. Oil does the same thing. So a high viscosity index number means that the oil is not going to thin out as much at higher temperatures or not going to thicken up as much at low temperatures. So higher viscosity index number means you probably got a little bit better behaving oil. Specific gravity, we're talking about density here. Again, scientifically a little more complex than how heavy it is, but in a nutshell for 30-minute webinar, our specific gravity is how heavy the oil is compared to water. Water has a specific gravity of 1. Most of our lubricating oils are going to be less than that. There are some that aren't, but a large majority of the oils you're going to deal with are going to have a 0.8, 0.9, 0.6, something like that. It's going to be less than 1, meaning that the oil is going to float on top of water, which was very convenient and lucky for us with some of the oil spills we've had on the ocean. the XL and Valdez that happened many years ago. Probably date myself by saying that one. But anyway, any kind of oil spill, we were lucky that the oil was actually lighter than the water because cleaning it up off of the surface of the ocean was much easier than it was going to be to clean it off the bottom. So usually our specific gravity of our oils are going to be lower than water. And meaning also in our machines, if we get water intrusion into our machines and our reservoirs, that's going to be found at the bottom, which is also convenient because we can put drain valves on there and remove some of the free water that's settled to the bottom. Next point we're going to talk about is flash point. So flash point of an oil is basically they will heat up to test for this. They'll heat up a cup of oil in 5-degree increments. And the point when that oil gets to the where it creates enough vapors above the surface of the oil where they can temporarily ignite with an ignition source, that's the flash point. If you were to go further and keep heating that oil up, you'd hit a fire point to where the vapors created are enough that it sustains a flame. That would be a fire point. But we really just want to be below that flash point. Very important for if you got high temperature type applications to make sure our flash points are good enough that we're not going to have any kind of flashes or explosions in either engines or industrial type equipment. The next point we're going to talk about is pour point. So pour point of an oil is basically how well it's going to flow in extremely cold temperatures. I live in the Midwest, so our wintertime temperatures can be very cold, which this pour point becomes very important with our oils. You get some of these negative degree weather. Oil doesn't want to flow in that. So this pour point value is basically telling you how well it will flow in very cold temperatures. And then the last point we're going to talk about, there's a ton more, but the main points I wanted to hit today was the oxidation stability. So oxidation is a process that happens when oil is exposed to oxygen. It will oxidize. We can't stop that process. We can slow it down, and that's what the goal is to try to do with our oils, is to slow that oxidation process. If you think about when you cut an apple or a banana or something, you leave it out on the table, it starts to turn brown and it might start smelling funny. Oil does the exact same thing. It will darken and it will start to smell bad, but other things will happen that won't happen to your fruit, like the viscosity changes and it just becomes not a very good lubricant. So we want to slow that process as much as we can. Additives are chemicals that are mixed with our oil, and they're there to basically designed to remove these unwanted features of oil and improve some of the characteristics so that it just behave better. A regular base oil just coming out with no additives put into it might be a decent oil, but there may be certain things that we want to address that we need to add lubricants into them. So most of your finished lubricants that you buy off the shelf, they're going to have at least some additives in them. Most oils have additives. All right, now that we've covered some of those, let's hit the first myth here. Moisture in oil analysis is not that big of a deal. Having water in our lubricants is fairly common, and it has little effect on the bearing life. That is simply not true, unfortunately. These charts here kind of show us, I've got 3 graphs here kind of displaying. All 3 of these have one thing in common. The y-axis is the bearing life in percentage. So let's look at the top one first, the effects of misalignment. With this chart, it's showing that we could get 100% of expected bearing life if we had 1 mil per inch or less of misalignment. We don't always get that. We want to get as close to that as we can, but the further away we deviate from that, the less life we're going to get out of that bearing. So if we look at the far right of that chart, we've got about 5 mils per inch, and we're down to under 40% of that bearing's life. So and that's one of the misconceptions I want to talk about too, is everybody's level of acceptance of failure. When we talk about all these things in our seminars, be it vibration or lubrication, we're trying to tell you what the best world-class situation would be if you have unlimited resources and money and time and people. This is where you want to be, and you want to strive for that. But we realize not everybody can get there in one step. You take small little steps to get there. But this concept is good to know anytime you're sitting through any of these kind of predictive trainings, whatever type of class it may be, is to realize that when we tell you the effects of these things are bad for your equipment, I know it's easy to think, well, we've had this forever and we're doing fine. Well, are you doing fine? Because the point is, it's kind of like my dad used to say, there's only so many switches, flipping that light switch off and on when you're a kid, running around being a brat. There's only so many in there, you're going to destroy it. And because I was a little kid thinking just the next hour, the next day, I wasn't thinking far out in the future. I didn't care about the future of that switch. I wasn't thinking about repairing it. But now when you get into this world, you do. You start to think, okay, if I'm getting 5 years out of this bearing, what if I could get 10? And it's these steps that you're going to take that are going to help that. So when I say misalignment's bad and it'll destroy your bearings, I don't want you to think, oh yeah, I've had bearings out of alignment for a long time and we haven't had that big of a deal. Just think what you could get, what kind of life extension you could get. All right. Now that I've said that, on to the next thing. The particle contamination is the bottom right graph in this picture. And we get about 100% of the bearing's life at about 12 microns. That's because most bearing manufacturers were kind of expecting people to use 12 micron filtration systems. That was just pretty standard. But you look at this one, we can actually improve the life of that bearing further than what it was actually designed to do by switching to like a 6 micron filter. We get rid of some of those smaller particles that can get into these tight spaces in these rolling elements and cause the problems. And we can improve the life. It looks like if we go from a 12 to 6, you're going to get about 150% of that bearing's life. So we can actually get more than what it was designed to do. So particle contamination is a big deal too. Even though the myth I was directly talking about was water, I do want to make that point that I've seen a lot of people pull oil samples, hold the bottle up and look at it, and I don't see any particles, so it's pretty clean. The particles that do the most damage generally are the ones that are smaller than what we can see with the human eye. So that's why going from a 12 micron to 6 micron can improve that life quite a bit. All right, so back to the myth, the water part. You look at this chart, 100% bearing life, and that's at 0.025% water and oil. That's a very small amount of water. At the far right of this one, we get about 20% of the bearing's life by just being 1/4% of water in it. So it takes very little water to reduce the life of that bearing. So bearing or water doesn't mix with oil with a darn, and it doesn't mix with our rolling element bearings very well either. It does not play well. Myth number 2. So the only real difference between mineral oils and synthetics is the price. An oil is an oil. So long as the viscosity is the same, it doesn't matter. It's an easy one to misunderstand, but there is definitely, sometimes you get what you pay for. This is one of those examples where you can. So comparing mineral oils to synthetic oils, mineral oils are generally crude type oils pulled from the ground. They're put through a refining process. And depending on how much refinement you do, it depends on how clean it is and how pure of an oil it is. There's basic groups on the next slide I'm going to show you. It's kind of broken up. The API created these different groups. The lower the number group of your oil, the less refinement it's had, the dirtier it's going to be, the more unwanted molecular structures are going to be left in it. So the molecular structures, mineral versus synthetic, the structures are going to be all different shapes and sizes in a mineral oil, whereas they're going to be very repetitive, very similar type size, which improves the oil's capability of flowing and lots of other things. The purity, mineral oils, like I said, depending on how much refinement they've gone through, they will still have some of these unwanted molecular structures left in them that we don't want in our oil. Whereas synthetics, we're designing that in a lab situation where we're not putting any of those in there. It's very pure. The cost, of course, so far, synthetics are still more expensive than our mineral oils are, but again, it kind of goes down to the bang for your buck. Viscosity index, remember I said the higher the number for that one, the better the oil is. That means if it gets really hot, it doesn't thin out as much. If it gets really cold, it doesn't thicken up as much. Synthetics, just without any additives put into them, they behave better in temperature changes. Toxicity is one of those things that depends on the synthetic. It can be higher than synthetic. Not all synthetics are toxic, but certain types can be. So mineral oils would be a little bit safer that way. Oxidation stability. So how quickly this thing oxidizes, turns brown, starts to go bad. Synthetic oil behaves much better too. So they will last longer. So you may hear people talking about whether in your engines, are you using mineral or synthetic? The main thing is it depends on how often you're going to change your oil. If you change it frequently enough, it really doesn't matter. But if you're in a condition where you can keep it fairly clean, a synthetic oil will last longer because it doesn't oxidize as fast. And then the last thing between the two is the mixability or solubility. So when we put additives into these oils, mineral oils tend to hold those in suspension a little bit easier, a little bit better because of the various different molecular shapes and sizes. Where synthetics, over time, if left unused, those additives could fall out of suspension. Now, I'm not talking about most places you're going to go through your stock fast enough, not going to be an issue anyway. But if you had things that were barrels that were stored for years, you may have an issue with additive separation if you have synthetics. like I said, usually not an issue anyway if you go through your stock quick enough. So here are those groups I was talking about, group 1 through 3. Just the third one, they're refined so highly that they're basically almost a synthetic oil. The fifth group is just kind of a catch-all group for anything that doesn't fall into groups 1 through 3 or 4. So groups 1 through 3 are all our mineral oils. Group 4 is our synthetic oils. And you can kind of see the chart there, comparison. Viscosity index is better. The amount of leftover stuff in there, that's where a lot of our differences are. Okay, myth number 3. When switching from one brand of oil to another type, the only important thing that needs to be the same is the viscosity. Additive packages may be slightly different, but they're inconsequential. Also not true. So first of all, what are additives? They're chemicals that are mixed with our oils to improve the performance of the oil. They typically make up about 0.1% to 30% of the oil. So it's a small portion of the ingredients in a finished oil, but they're there to either act on the metal surfaces in our machines or within the oil itself. Depends on what the additive is and what it's designed to do. So list of some of the major additives that are used. This is not an all extensive list with everything, but some of the major players in a lot of our finished oils. Antioxidant being in almost every type of oil that you're going to find. There's a caution with this. This is why I put this up there with that myth that we can't just use these as if the additives have no effect on anything. They do. One of the things I would caution about is some of these antioxidant additives, as ZDDP. It's made of zinc and phosphorus and some other stuff too. And it basically does not react well with galvanized materials. So if you have any kind of an old oil storage container that's made of galvanized material, you might want to think about swapping that out for either a different type of metal or plastic or something, because those additives could react with that and that could cause some problems. Rust and corrosion inhibitors are basically designed to make a film on the surface of our metal parts in our machines so that if water does get in there, it's not making direct contact with metal, so it prevents that rust and corrosion. These VI improvers, that stands for viscosity index, that's just designed to improve the oil's ability to resist changes with temperatures. And then these two next ones are important. The anti-wear and EP additives, they actually behave very similarly. They're a similar type of additive. They will also make a film designed to attach to the metal surfaces. They're polar, so they get inside our machine in the oil and they mix around and they stick to the metal surfaces. They create this film. That film is there to design basically to, if we get these boundary lubrication conditions or lack of lubrication, that when metal to metal surfaces make contact, instead of metal to metal, we have that surface film on each of the metal components, that is the sacrificial layer. Now, the main difference between these two, and this is where I want to caution people, is if you're using an anti-wear oil and you wanted to switch to an EP additive, please contact your lubrication supplier first or original equipment manufacturers. Check that first. There are some EP additives that do not behave well with yellow type metals like bronzes, brasses, coppers, things like that. Some pinions and gearboxes can be made of that. You can actually soften that material and you can wipe the gearboxes. I've actually seen it happen at one of the places in the past. So be very careful switching to an EP additive. Ask first. Usually like I said, your supplier, they have answers. It's a lot faster to get answers from them than it is to try to look it up on your own. Usually they have this information. So check before ever switching to an EP additive. Be careful with those. Detergents and dispersants are generally used in engine oils. They're there to keep deposits from forming on our engine surfaces. We have anti-foaming agents. These are designed if you're in a high flow type circulation lubrication system and you have problems with foam, you can add these anti-foaming agents to it. And essentially what some of these are they're just very small, like 5 micron size or smaller, soft little particles that you intentionally add to your oil. But because it's a particle, you have to be careful. Some of these will say, do not filter less than 6 microns because you might remove that anti-foaming agent. So less of an issue than the other ones. The main thing to take from this list, though, is that EP additive. Be very careful with those. Tackifiers, if you've ever went to AutoZone or O'Reilly and seen little plastic gears that you can crank and the one sticks to it better, that's the use of a tackifier additive. That additive helps the oil stick to those gears better without flinging off. That's what it's designed to do. Then we have emulsifiers and demulsifiers, which these additives are both designed to either A, separate the oil and the water so they stay separated more easily and you can drain off the free water, or they're designed to glue the water to the oil. Engine oils a lot of times have these. So if you pull off your oil cap in your engine and you look at the inside of that and you see that white gel, I'd be looking to consider to have that thing looked at into, because that gel is formed from those emulsifiers in the oil, and it's mixing with either water or it could be coolant. And if it's coolant, you may be looking at a cracked head or a head gasket problem. So you see that gel, that's what those emulsifiers, that additive is doing, is trying to keep it suspended so it's not sitting on the bottom of your pan and rusting things out. So if you see that gel, be cautious. Time to start looking for a new car, probably. Anyway, last thing, pour point depressants. We talked about the pour point of oil, how well it flows in really cold environments. These are just designed to help that happen a little more smoothly. Okay, myth number 4, grease is grease so long as it stays in place around the bearing and is replenished at the right frequency. It doesn't matter what type you use. I do see this quite a bit. People just grab a grease gun, whatever's in it, it's good enough. It's grease. But man, that's where you can go very wrong. So some information first. I think I mentioned this before. Grease is mostly oil. So the first thing I'd always want you to do too is, this is another fact that goes wrong, is people, they purchase grease based on just a title that says this is a universal grease, and it's an NLGI2. I was told to use an NLGI2. That NLGI number is basically only telling you how thick the thickener is in the oil. It doesn't tell you anything about the actual oil itself. So that's the most important part. So if you got an ISO 32 or an ISO 100 oil base in your grease, that's the important number to figure out first. We want to make sure the oil is right to make the right lubrication for the application. Then you can worry about whether the NLGI number is a 1, a 2, a 3, or whatever. That's just how thick that thickener is. Okay, so that part cleared up. We've got a couple different types of thickeners that are used in the United States, or across the world actually, but lithium-based, calcium-based, and aluminum-based thickeners. Those are your common, everyday type greases. Then we have a polyurea grease. Polyurea grease is typically used primarily with electric motors because of its properties of not being corrosive to the insulation and things like that if it gets in the windings. So those are the 4 basic types. There's more than that, but those are the 4 main types of grease that you're going to see out there, the different types of thickeners. I also want to caution, there's no nationally recognized color coding system for grease. So if you buy a red grease from this manufacturer and buy another red grease from another one, chances are they're not even at all the same. Matter of fact, you can usually, with some grease manufacturers, you can ask for them to dye it a certain color if you want it to be a certain color. So do not fall into that trap to where, hey, a red grease is a red grease, a blue grease is a blue grease. They may not be the same at all. And then the next huge problem is what this whole myth was about, is I can use any grease. The thickener that's used in these greases can be very incompatible with each other. If you mix incompatible greases, it's either going to harden in place and not behave very well as a lubricant at all, or it's going to soften up and possibly drain away and have a dry bearing situation. So be very cautious with mixing different types of grease thickeners. Pick the one that you should be using and stick with that. Make sure your grease guns are either A, labeled with what type's in there so you don't cross-contaminate, or B, use the clear tube bodies so you can see what tube is in there. And then there's other types of fittings you can use, like grease zerks on machines. If you want to make sure that people aren't using motor greases for fan bearings, you can do button type or hydraulic type fittings. You can change those out so that you can't cross contaminate with that. But various different things. One other thing before we move off of greases too, people that use electric grease guns, battery operated or pneumatic, air powered, I would caution using those. There's places where they're fine. If you've got slow speed bearings where there's no shields or seals in place, and it doesn't matter if you over grease it a little bit, that's fine. But I will say with high speed stuff and electric motors, I would highly recommend using a manual pump grease gun, because grease guns can create about 15,000 PSI. Some of our bearing seals, shields, our cages around the rolling elements, they can bend or be damaged at much less PSI than that. So With a manual, as you're pumping, you feel that lever, you feel that back pressure, you know to stop. With a battery operated one, you hope that the pressure relief valve works and that it doesn't add too much pressure, but we don't know. So that's why I would highly recommend switching. Just go back to the manual grease guns. Unless, like I said, head and tail bearings on conveyors, very slow speed things that the worst case scenario, if you overdo it, is a mess. Sure, you can still use battery operated ones for that. All right, last myth. Um, Collecting oil samples is an easy task. You can send pretty much anybody out there to do it. It's simple. Just like any other of these predictive technologies, unfortunately, the data collection process is just as important as any of the rest of it. It's the first link in the chain, and if you screw that part up, you screw up your entire data. So, whoops. Garbage in equals garbage out. So sampling, there's a couple key things to take away. We want to take a sample from an actual good representative place in our system. So if it's a reservoir with it's not a circulating system, it's a sump or something like that, you want to pull somewhere from the middle. You don't want to pull off the bottom where all the sludge is. You don't want to pull directly clear off in the top. We want to be somewhere in the middle. If you're using drop tube sampling, vacuum sampling, you got your little white hose you're dropping in there. Be careful. That tube comes off of the spool. It wants to stay around. It wants to go against the side of your gearboxes and things. It's hard to see where it's going when you jam it down that hole, which could be a safety factor too. I have seen where it has got between gears and pulled the little tube out of the sampler, and now the tube got chewed up between the gears. Luckily, it's soft material. It didn't damage anything, but it's something to be cautious with. There are fittings and things, mini mesh valves, pitot tubes, various different things that are on the next slide I'm going to show you that are good, better ways to take these samples. But sometimes we have to do, the best with what we have. So drop tube sampling, it sometimes is a necessary evil. But a couple of key points, like I said, take from a representative area. Don't take from the bottom. I've seen lots of places that take samples from the bottom of just the drain plug. The problem with that is, yes, you are getting a maximum data density. All the stuff that's been in there is sitting at the bottom. You are capturing that. But the thing is, if it's not actively circulating around the bearings and sitting on the bottom, it's not hurting anything. It's down there. It could be from a previous failure. You might have metal particles down there from a previous failure. You pull a sample off that, you might think your gears are going out when in fact that was from several rebuilds ago and it just got stuck in the system. So we want to pull up off the bottom. Pitot tubes are one way to do that. It's basically just a little piece of tubing that you can run up through the bottom. It's like a straw, and you can bend it to whichever direction and area of the sump that you want to pull from. Also, don't pull from after filters. There's no point in doing that unless you just want to test to see if the filter is working, because the filter's there to remove particles. Well, it's removing particles that we want to see that's floating in our oil. So upstream of filters, not off the bottoms. Anywhere where there's active movement in our oil, that's the places to be taking these samples from. Also, how we treat the sampling hardware. Make sure it's clean. It's kept in a clean place. The lids on our sample bottles are on until the very last second and put back on as soon as we're done collecting the sample, because there's stuff in the air, humidity, particles in the air, dust, things like that. So here's some of those various different types of mini mesh valves and sampling ports that we can install. Yes, it's an upfront cost, but you're getting very repeatable data. It's coming from the same spot, and there's less chance for cross-contamination. All right. That is it. I guess on to any questions.
Yeah, I know we've gotten a little bit right here at the time mark here, so we'll spend maybe the next 5 minutes or so. If anybody has a question, just either unmute yourself or kind of raise your hand. There's a button at the top, so we'll spend a little bit of time answering questions, but we respect your time and don't want to just pretend like we have an unlimited amount. So, um, does anybody have any questions for Brett or anybody here?
It's our first public course. Do you have that off the top of your head, David? Is it
For the
October?
lubrication? Yes, is
Yeah.
July 30th through August 2nd in Charlotte, North Carolina.
Oh, right.
Yes. Mm-hmm.
So, and if anybody certification wise, we provide our own certificates for that that follows the ISO 18436-4 standards. But also it would prep you if you're one of those types that wants to have that ICML, MLT1 or MLA certification. Going through our class will get you what you need to do to sit through that certification. All
All
right, I
right.
did see.
I see one
Hey,
question came up from Adam Lunt. Could you talk briefly about the benefits of ultrasonic greasing? He put that in the chat. So if you've got a question,
yeah,
maybe type it in the chat there.
yeah, ultrasonic racing's a lot of people are starting to finally pick up on that. Lots of good tools out there to use for ultrasonic racing, but essentially, to keep this fairly brief, the idea is that we're going to listen to the bearings to determine when it needs grease rather than just doing it time based. Time based, obviously, I think a lot of us have realized that if we do time based, especially with electric motors, there's a good chance we're over greasing these motors and we're actually causing more damage than we are um, by under greasing. So ultrasonic, we're just listening to the ultrasonic range while we're pumping the grease in to let it tell us when it's had enough. That's in the simplest form, but like I said, lots of good devices out there. Some of them walk you through step by step how to apply the grease, when to stop. Some of them are simple as you just listen and monitor a decibel level yourself. But it's a very good tool that can save you lots of damage to, especially electric motors or high speed fan bearings and things like that.
Very good. I see Roberto raised a,
Yes.
yeah, there
Can
you
you
go.
hear me?
Yes, gotcha. Yes.
So this is related to the ultrasonic gun. So obviously, when you use the ultrasonic gun, the asset or the equipment needs to be running, correct? But what happens when? So what is the best way to calculate? If the machine is not running, obviously you cannot use the ultrasonic gun. So what is the recommendation? How to find out how much? What is the correct amount of grease that you need to add to that piece of equipment? Again, you cannot use the ultrasonic gun. So what is the best recommendation?
If you can't, well, first thing I want to mention is like if it's not running, ideally we'd want to grease everything when it's running. But back to if you don't have an ultrasonic gun and you wanted to do proper greasing, there are various different, which you can find a lot of these on Google, but there are various different lubrication calculators out there. Basically, there's even an app that I have downloaded to kind of get you in a ballpark. I would say you have to be cautious with these, but they're at least something, because some of these will give you, they calculate the volume that the bearing actually has, how much space it has to put grease into. But obviously, we don't want to fill them entirely full because that would be too much. So
Mhm.
a lot, you got to find out which calculator that you're finding, which I think some of the bearing manufacturers, if you go to their websites like SKF and FAG and I don't know. I think there's a few others out there. I can't think off the top of my head, but they have their own calculations that you should follow based on dimensions of the bearing and what speed it's turning at. And once you get that, then you get a number of, hey, this volume. A lot of these will even tell you what frequency. So the app I found, I believe it was free. LubeCon, I think, was that specific app. I don't necessarily promote one over the other, but that's one I found. The LubeCon app, you can tell it the bearing type, which sometimes the number might be a little challenging to get the bearing number, but if you have that, you put in that bearing number and it will tell you, we recommend this much, this amount, and this often. And then, like I said, I would take that volume and I'd be careful with it. I usually would use about half of whatever it said, especially if it's a motor, or even less, because we definitely don't want to overgrease motors. Certain pillow block bearings, especially if they're slower speeds, not as big of a consequence if we overgrease it. So that's a little bit different. But that's, I guess, the best answer I could give you. There's no real clean, great answer for, because there's such variety of different sizes, shapes, sizes, and speeds of bearings that we use out there. Does that help at all?
Yeah, thank you.
A great question there, Roberto. Anybody else have any questions? Yeah, not a problem there. So we definitely thank y'all each and every one of you for joining today for our first in our summer webinar series. We look forward to next month. We'll have Robert Scarrick presenting on our 4.0 materials. So talking about the wireless technologies and different systems like that, and the importance of what they do and how what can be offered with those. So we'll be watching for some communication coming out about those. And again, we thank you each and every one of y'all for joining today. And if you've got any questions, definitely let us know. Feel free to reach out to me. My email is D as in David Barry at technicalassociates.net, or anybody else on our team. You can find all that information on our website, technicalassociates.net. Again, thank you so much for joining us today. Thank you, Brett, for presenting there. Did a great job. So if that's it for everybody, we'll just see everybody next month.
Thank you. Thank you. In the name of Hydro, we appreciate your information. So very informative. Thank you very much.
Great.
Thanks,
Sounds
guys.
good. Thank you, Roberto.